There are several ways to produce nanofibers of different attributes and applications: template, synthesis, phase separation, self-assembly, nanofiber seeding, and electrospinning. However, electrospinning is regarded as one of the best and most popular techniques. Electrospun materials exhibit diverse and exponential physical and chemical attributes differentiation from scaffold fabricated through their fabrication methods. Nanomechanics properties of PLLA has a higher adhesion force and elastic modules. By using the atomic force microscopy AFM technique, the polymer chains become more compact and ordered under both compression and shear stresses. The atomistic approach is the most common technique used to investigate the structural crystallization of polylactic nanofibers. There are at least two structures that can be formed for solutions spun poly L-lactite nanofibers. These two structures depend on the drawing and spinning conditions used in the fabrication of nanofiber material. The pseudo-orthorhombic alpha structures have chains in the unit cell. It's imperative to note that this type of structure is generally found at a comparatively low drawing temperatures. They can also be formed in a low hot drawing ratios. The second structure of poly slash L slash lactide nanofibers is known as the beta structure. As opposed to alpha structures, beta structures are generally formed at a relatively high drawing temperature. Alternatively, beta structure of poly/lactide nanofibers can also be formed at a higher hot drawing ratios. As opposed to the alpha structure of polylactide nanofibers, the beta structure of polylactide nanofibers has an orthorhombic unit cell which is composed of 6 chains. The chain conformation of alpha structures of polylactide nanofibers are left-handed 10^3 helix. On the other hand, the chain conformations of the beta structures of polylactide nanofibers are left-handed 3/1 helix. As the picture shows on the left, the alpha structure -10/3 helix being waxed patterns with fiber. On the other picture on the right, showing beta structures -3/1 helix being waxed patterns with fibers. As we see on the left picture, it's a waxed patterns of tilted fibers showing the meridional reflection of alpha structure, -10/3 helix tilt by 15 degrees. On the right pictures, we can see waxed patterns of tilted fibers showing the meridional reflection of beta structure, -3/1 helix tilt by 15 degrees. As such, the preferences and choices between one of the two structures are usually determined by pattern considerations. It's significant to note that in fiber materials containing beta and alpha structures, the beta structures seem to bear a significant amount of the load than the alpha structure in experiments of stress and strain. Experiments were done using meridional small-angle X-ray scattering techniques demonstrate a maximum for fiber materials that have only alpha structure. Thus, it can be concluded that alpha structures assume lamellar folded chain morphology. On the other hand, the beta structures seem to assume fibrillar morphology when subjected to the same experimental technique.
The properties of electrospun material can be characterized into 4 different groups. First, mechanical properties. In a study performed to evaluate the mechanical properties of electrospun nanofibers and their composites, bending, tensile, and impact strength assessment were used. The currently available electrospun materials exhibit real challenges such as poor mechanical attributes and inability to alert specific mechanical characteristics for various applications. There are various techniques used to enhance the mechanical and handling attributes of electrospan nanofibers. Cross-linking has been used to enhance both the flexural and tensile strengths of fibers. And additionally, scaffolds that have been linked with the Gimkin demonstrate enhanced morphology and extra mechanical attributes. In the physical and chemical properties, the correlation between the tensile strength and the content of grafted hydroxylated GHAP was demonstrated. It was discovered that all the components made from a combination of PLLA and GHAP exhibited a higher tensile strength about those composites made from a combination of PLLA and HAP. The assessments were performed for annealed specimens. It was also discovered that the tensile modulus of the composite material made from electrospun nanofiber increased as the particle content increased, regardless of whether the specimens were annealed or not. The direct increase in the tensile modulus and the electrospun nanofibers is attributed to the successful reinforcement of the composites by HAP or GHAP particles. In the biological aspect, one of the major benefits of electrospun nanofibers of PLLA is their ability to favor cell attachments due to their higher surface area to protein absorption. The binding sites of nanofibers have improved the ability of the nanofibers to favor cell attachment as a result of large surface area.
Fabrication of nanofibers scaffold. Electrospinning was used to prepare nanofibers scaffold. The 12% solution of PLLA was placed in 5 milliliter syringe that was connected to the 21 gauge needle through extension tube. A steel grounded collector was used to collect the electrospin nanofibers in a distance of 15 cm from the needles. The solution was fed through the tube into the needle by syringe pump with a rate of 1 mm per hour. Application of 20 kV voltage between the needle and the collector forced the solution droplet to leave the needle and deposit on the cylinder in the form of the ultrafine fibers. Having reached a thickness of about 200 micrometer, the mat was detached from the collector and placed in the vacuum for the evaporation of the residual solvent. Oxygen plasma treatment was then performed by a low frequency plasma generated of 44 GHz frequency with the cylindrical quartz reactor. Pure oxygen was introduced into the reaction chamber 0.4 MPa pressure, and then the glow discharged with the agent for 5 minutes. Because Bristan PLLA nanofibers show a free low capacity for cell attachment due to the high hydrophobicity.